Today we will be discussing mass spectrometry. Mass spectrometry is an analytical method used to determine the composition and structure of ions based on the mass-to-charge ratio of its little constituents. This data is shown as a spectra. So let's begin with a brief history of mass spectrometry. So the idea of mass spectrometry, or MS for short, was first discovered by Sir J.J. Thomson in 1913 after observing a stream of neon atoms deflected through an electric and magnetic field onto a photographic plate, proving the existence of isotopes. The deflection of the isotopes of the neon atoms was discovered to be based on the mass-to-charge ratio of the atoms, a discovery that is the basis and foundation of MS as an analytical method. Although Sir J.J. Thomson is credited for inventing the first MS, Arthur Jeffrey Dempster is responsible for developing MS as an analytical method, and the modern version of the MS, incorporating electron impact ionization and magnetic focusing to improve accuracy and resolution of measurements. In 1919, Francis William Aston further improved the design of the MS to further increase resolving power to effectively study and identify different isotopes. And over the course of the next century, further discoveries kind of lead to the improvement and development of different types of mass spectrometry that we know of today.
To actually create a mass spectrometer, you need to answer two questions. The first is, how are you going to ionize your sample? And the second is, how are you going to separate your sample, which is all going to have the same kinetic energy, but potentially different parts are going to have different mass to charge ratios. There's a couple of answers for the first question, and the most common is electron ionization. Electron ionization is essentially when you shoot an electron beam at your sample. This results in your sample being ionized, but it can also result in fragmentation of your sample, which is sometimes desired and sometimes not. When it's not, you can use chemical ionization. Chemical ionization is more gentle because you combine a small amount of your sample with a large amount of gas. Then when you ionize your sample and this gas, you're going to have many more gas molecules than your sample, so it's much more likely that the gas will be ionized and the gas itself will do the ionizing of your sample, leading to less fragmentation. To answer the second question, there are also a variety of methods, two of which are the time of flight and the magnetic sector method. The time of flight method relies on kinetic energy and the fact that all of your sample is going to have just about the same kinetic energy. This means that heavier particles in your sample are going to be moving slower. And ultimately, this means that the fastest particles are going to reach the detector first and the slowest last. And this is how you separate your sample. The magnetic sector technique relies on the interaction between electricity and magnetism. When a charge is moving through a magnetic field, it feels a force that is orthogonal to both the velocity of the charge and the magnetic field. If you set up a curved pathway, then only certain particles will be passing through that pathway based on their mass to charge ratio. And you can tune which particles will pass through based on the magnetic field strength. Ultimately, how you answer these two questions is going to be based on the strengths and weaknesses of the different techniques. And these techniques ultimately determine whether you use a time of flight, whether you use a magnetic sector, or a different technique. Often you'll see proteins analyzed with time of flight, and other stuff analyzed with the magnetic sector.
3, 2, 1.
So what is MS useful for? There's actually a lot of applications which make MS one of the most useful analytical tools in chemistry. It can be used to give you information on the molecular weight of a compound, the molecular structure. You can find out what elements are present, and also study reaction kinetics, although there are more applications than just those. The types of materials which can be studied are both inorganic and organic solids, liquids, and gases. Using isotopic ratios is one of the most important things when you're trying to determine what elements are present in your sample. One example of this would be chlorine, which has a 3-to-1 ratio of chlorine 35 to chlorine 37. So if you find that in your spectra, there's a good chance chlorine was involved. So the peak areas you find are also proportional to the amount of ions that have been detected, which is another way where you can determine what elements are present. This makes MS both good for qualitative and quantitative analysis. And the quantitative detection limit is in the part per billion range, making trace analysis possible. When you want to identify the molecular structure of your compound, it is really helpful if you can identify the molecular ion peak, which is your total molecule in its ion form. If you can't identify the molecular ion peak, it is still very helpful to identify fragmented peaks, which have come from ions that have fragmented off the total molecule. Using a basic knowledge of chemistry, you can assign different peaks to stable ions, and hopefully from there determine what your molecular structure is. Reaction kinetics can also be studied with MS. This is done using tandem mass spec in multiple fragmentation stages. The number of fragmentation stages used is designated by a superscripted n. So if you had 3 fragmentation stages, you would have a 3 there. This is usually done using a Fourier transform mass spec or a quadrupole. And analyzing how the chemical composition changes with time is how you study the reaction kinetics. There are several limitations when working with mass spec. One of them is that the materials being analyzed need to be volatile. They need to evaporate easily under standard conditions. If they don't, specialized ion sources need to be used to account for this. Another main problem is that you need pure compounds. If you don't, the spectra you obtain will be very difficult to read because there will be too many peaks. So this is one of the reasons that mass spec is often coupled to GC or LC.
Over the past few years, there have been many methods developed to improve MS. One method developed recently is known as stir-bar sorptive extraction, which is mainly used to analyze contaminants in environmental water systems. The main use of this method is to concentrate pollutants in water samples, since the pollutants are usually in concentrations that cannot be detected by the MS. In this method, a stir bar is coated with a thin layer of polydimethylsiloxane, usually around 1 millimeter thick. The stir bar is then subjected to a water sample of interest and stirred for several hours to allow the contaminants to become absorbed onto the surface of the stir bar. The stir bar is then removed from the sample and placed into a smaller volume of solvent. The contaminants are then cleaned off from the stir bar through various methods, such as sonication. The solvent, which contains a higher concentration of pollutants than the initial water sample, is then analyzed using either LCMS or GCMS. Through this method, many research groups have been able to detect contaminants in real-world situations. One example is the Albufera Lake in Spain, where a research group was able to detect many pesticides in the water, such as atrazine, phenthine, and diazinon.
And that was a brief overview of mass spectrometry. Hope you enjoyed the video.